This might be long, but let me tell you what I'm going to do. This is a review. Everyone wants a review day. I'm going to do a review day for all the big ideas and none of the small ones for the things that you need to be ready for the final exam. So this is for who would want to watch this video? One, my mom. Hi, Mom. Just kidding. She doesn't watch my videos. Not that I know of. But it's my students in physics class, students that want to review, students getting ready to go into the second semester. This is the first semester calculus-based physics course. And in fact, I am using this book, which is the best book ever, Matter and Interactions by Ruth Chabay and Bruce Sherwood. Great people. So if you're not using that book, I mean, some of this it's all the same physics. You just may have different notations. Okay. And I don't really know where I'm going to go. I'm going to try to do as much as I can. I don't have a plan. So I do have some breaks. I have 3 breaks planned where I will show you something just to give you a little mental break. Okay, let me just start right away with the 3 big ideas. These are huge. Okay, if you break this course, and this is the first semester calculus-based course, so it doesn't include the second stuff, which is electric and magnetic fields. The 3 big ideas are, number 1, the momentum principle. I shouldn't even write that out because it takes too long, but maybe it doesn't take too long. So this says that the net force on an object, on a system, is equal to the change in momentum divided by the change in time, where momentum is technically defined as this. Mass times velocity vector divided by the square root of 1 minus the velocity squared over c squared, where c is the speed of light, 2.99 times 10 to the 8th meters per second. Now, if the velocity is really, really, really slow, like the fastest bullet you could ever shoot, then v over c is essentially, this is going to be, in your square, it's going to be essentially 0. So I get p is, in most cases, going to be approximately equal to just the mass and velocity. So this says the change in momentum divided by the change in time is equal to the net force. And really, it says something important. It says, what do forces do? Forces change momentum. Change. So delta here, delta p literally means p2 minus p1. It's the final momentum minus initial momentum for that same time interval. So delta, we use the Greek letter delta to represent change. Okay. That's the momentum principle. There's a whole bunch of stuff to talk about there, but I want to go over the 3 big ideas. That's the big idea. Number 1, momentum principle. We probably did 60% of the class I did focused on the momentum principle. The next is the work energy principle. This says work is the change in energy. I know that one's easy, right? Now, what is work? Well, if you have a force applied over some distance, the easy definition is to say work equals F dot delta R, where delta R is the displacement and F is the force. Now, this assumes that the path is straight and that the force is constant. But if that's not true, then you actually have to integrate a line integral from 1 to 2, from point 1 to point 2. We can describe that in lots of different ways, of F dot dr. And if you don't know how to do that, I don't think at this point, we're trying to get ready for the final exam. I don't think this is a deal breaker, okay? But you should be able to do this. So what about the change in energy? Well, we can have lots of types of energy. We can have particle energy, which is E equals mc squared over the square root of 1 minus v squared over c squared. This is really, this says that all particles have energy based on their velocity and their mass. This is like this, though. These are the only things that we really need to worry about for atomic level or super fast. Okay. Then there's other types of energy that I'll get into later. The most common one is the kinetic energy, which is approximately 1/2 mv squared. Now, I do want to say this, because there's an important connection between these two. So let me write this as delta P. So I have delta P equals F net delta T. And then let me use this definition for the work, and I'll assume that we only have a kinetic energy for the change in kinetic energy. So I can say delta K equals F dot delta R. These are so important. I'm gonna break out my colors, right? I'm gonna put green around that one. And I'm gonna put red around the other one. I got some new colors just for you. So this is the momentum principle, just written in a different way. This is the work energy principle, written for certain cases. Okay, number one, you'll notice this has time. This doesn't have time. No time. Okay, so if we're dealing with a change in stuff and we know the time interval, then we're probably going to want to use the momentum principle. If we don't know the time interval, then we're probably going to use the work energy principle. Work energy principle does not deal with time. The momentum principle does. The other very, very big idea, and I'll talk about vectors in a little bit, but here I have the change in momentum, which depends on mass and velocity. Here I have the change in kinetic energy, which depends on mass and velocity. However, this is a scalar. This is a vector. So this is a vector equation. This, once I take F dot delta R, that's the dot product, which I will cover in just a little bit, then that is a scalar. So this is scalar, scalar, vector, vector. So those are the two big differences between the momentum principle and the work energy principle. And this gets a lot more complicated, but I'm just getting you started. I want to put this all on the same page, so I'm going to, just because, you know, you can't really stop me. And the last principle is the angular momentum principle. I'm going to write it out, just to be fair, because I can't write. Oh, I didn't. Okay, I don't have to. So this says that torque net O vector equals delta L over delta T. This says that torques on objects change the angular momentum of an object. Notice that this and this are very similar, right? Torque net, F net. Change in angular momentum, change in linear momentum, change in time. Okay, this also can be written as a derivative, and so can this, but let's just deal with the basics first. Okay, so now we need to know what is torque. Torque about some point O is RO cross F, and that's the cross product. And we'll talk about that when we get back to this. And then angular momentum for a point particle is RO cross P. Let me say this about the angular momentum principle. It gets complicated because we deal with these cross products. So it's a three-dimensional situation in the most case. The other thing is, in a lot of ways, we don't need this, right? If I have a point particle, I actually can calculate F and delta P instead of the angular momentum. But if I have a rigid object like a rotating pencil, or there's a pen, then I may want to treat this as a rigid object. And then it's just easier to deal with this in terms of angular momentum instead of 10 to the 28th individual points are moving around. Okay, so these are my three big ideas. I need a box around this one because it's only fair. I said 3 ideas, and I have 3 ideas. So that's, if you think about that in terms of the course, where are we? Angular momentum principle, work energy principle, momentum principle. And if you want to stop there, that's fine. That's where you need to be. Okay, now there's a whole bunch of little stuff that goes in between. So let's just get right to it. I'm going to try to go in order. The first chapter, I'm looking over here, my notes. Let's talk about average velocity and position. So position, velocity, acceleration. And really, in order to talk about this, you need to first talk about vectors. So a vector is a variable that has more than one piece of information. Okay, so if you think about something like time, mass, let me think of another one, energy. No, that one's not so easy. I'm trying to think of things that you can, kind of wrap your head around yourself. Time, mass, number, count. I guess a count. Why am I not thinking of other scalars? These are all scalar values. Okay, they're scalar in that they only have one piece of information. I just have the time. I mean, it has units, right? But that's not really the number. It just has one number. Vectors are things like velocity, position, acceleration. Oh, here's one. Momentum. I spelled that wrong. Okay. So these have three pieces of information. We could represent these as an arrow in 2 dimensions. So if I have this is my x and the y-axis, I also have a z-axis coming out, but I'm not going to draw that. Then I can represent this arrow as some, and it doesn't really matter what I'm going to call it. Let's call it the vector A. It's just a mathematical vector, so it doesn't have a unit or anything like that. So this is composed of part of it going in the x direction. I'll call that AX. Part of that going in the y direction, should have been a different color, AY, at some angle theta. So there's a couple things I could do. I could write A as the vector. The way I like to represent it and the way the book represents it is AX, AY, AZ. So this says how much of it is in the x direction, how much is in the y, and how much is in the z. And this is in Cartesian space. You could make vectors in polar coordinates and other coordinates, but it gets more complicated. We're not going to do that in this class. Now, if I know the magnitude, let's do that first. The magnitude of A, we define as the square root of AX squared plus AY squared plus AZ squared. And so this tells you the scalar length of the vector. It has the same units as the vector itself. So if you're dealing with a velocity vector, this would be a velocity. Position vector would be a position. Acceleration would be an acceleration. And these are the x, y, and z components. So this is just like the Pythagorean theorem in 3 dimensions, so it does indeed work. A lot of times we will write this as A. So if we put an arrow over a variable, that's going to mean it's a vector. If we write no arrow, it's a scalar. The better way to put these absolute value signs around it that look like absolute value signs, and that tells us the magnitude. Okay, what if I have this? This comes up every once in a while. What if I have the angle that we're dealing with this vector like this? In this case, I could say, since it's a right triangle and AY has to be perpendicular to AX, then I can say cosine theta is equal to the there's a hypotenuse, the adjacent over the hypotenuse, so it's going to be AX over A. So if I multiply both sides by A, I get AX equals A cosine theta. Sine of theta is going to be opposite over hypotenuse, AY over A, so AY equals A sine theta. Okay, so, and then the z direction, you could use spherical coordinates for that, but this comes up sometimes. It's not a big deal. Okay, now what can we do with vectors? I can add vectors. If I have another vector b, bx, by, bz. I feel like I'm getting too far in the weeds here. Then a plus b would be ax plus bx, ay plus by, az plus bz. So you just add the components. And whether they're positive or negative, that's fine. It doesn't really matter. Magnitude adding. You can multiply a vector by a scalar. I'm kind of losing it here because there's this. I don't want to do a whole lecture on vectors. But the most important thing is that two important things. If I have an equation like this, A equals C. That's a scalar vector vector. This says this side of the equation is a vector, that side is a vector. You can't have a vector equal to a scalar. That's not possible. Also, if you have a vector equal to 0, then you would have the 0 vector, which is the vector 0, 0, 0, which is not the same thing as a scalar 0. Okay, this one a lot of people just blow off, but it is important. Okay, let's go ahead and talk about position, velocity, and acceleration. Position is a vector. If I take my origin and I have some point up here, I can say this is the position. We use the vector r for that, and it's just a vector that tells you from the origin to the object where it is. One thing that comes up is this. Let's say it moves to over here. I'll call that r2. Then what I want is delta r. Delta r is going to be r2 minus r1, and so that's this vector, delta r, the displacement. Why do we care about that? Well, one, you'll notice that if I put my origin over here, here's my xy axis, then I have these as my vectors r's, r1 and r2, but I still get the same delta r. So delta r doesn't depend on where your origin is, but r1 and r2 do. Okay, so the origin is not real, so that's fine, because you don't really want to have a dependent on your origin. Why do we care about displacement? Because that is how we get velocity. Velocity is defined as average velocity. It's defined as the change in this position over the change in time, and it is a vector. And this is the average velocity. If you take the limit as delta t goes to 0, then this actually becomes dr dt, a derivative. And you can't take a derivative of a vector. You just have to take the derivative of each component. Okay, so just about everything we do in the class, we can get by with this. But if you're in calculus, I just want you to know that that does indeed exist. And that's the definition of average velocity. Now, there is another definition of average velocity that is important. The average is v1 plus v2 over 2. If it's changing at a constant rate, then we can use this for the definition of average velocity too. This comes up a lot when we want to find out how far something moved during a time interval. Then we use this average velocity. We may know the initial and the final velocity, so you can find the average. Okay, the last thing let me go over is the acceleration. So the acceleration is defined as the change in velocity over the change in time. And so that's also, you can write that as v2 minus v1 over delta t. Okay, so I'm not going to derive it, but I will say there is this kinematic equation that people see a lot, and it really comes from the definition of the acceleration and the two definitions of average velocity, and it looks like this. R2 equals R1 plus V1 delta t plus 1/2 a delta t squared. That's the kinematic equation that tells you where an object is if you know its starting velocity and it has a constant acceleration. That only works for constant acceleration. Okay, so that is position, velocity, and acceleration. How am I doing on time? Okay, I think it's time for our first break. I'm going to save the best, I think maybe the thing that you might think the coolest for the last. Let's see if you can see this. Yeah, you can see that. See that? You like that? It looks like a little tree inside of the glass. This is a piece of acrylic. And what they do, and I got this, I think in Pittsburgh at a conference. It was for some supercomputing thing, and they were giving these away just for fun. And so what they do is they take this and they put it right there, and then they shoot high energy electrons at the acrylic. And the electrons, this is an insulator, so the electrons kind of just get stuck in there, and that's it. But then what they do is they take a metal rod and they touch it right here, and they ground it. And then all the electrons get out of the cube. But when they do that, they make a current, and that current melts the acrylic in that path. So this is the path that the electrons take to get out of the acrylic, and you get that nice little tree effect. Isn't that cool? I think it's cool. Okay, it's a good thing to put on your desk. Was that a nice break? I was told you're supposed to take breaks. Okay, let's talk about the momentum principle. F net equals delta P over delta T. Okay, but what kind of forces can we have? If I have an object, let's say I'm gonna do something like this. Here's a block sitting on a plane. You can break this into two types of forces: long-range forces and contact forces. So long-range forces are forces that act on this block and they don't have to touch. And then contact is things that touch. Okay, so in this case, there's only one long-range force. A lot of times what we'll do is we'll draw a dot and then draw all the forces as vectors acting on it. So the gravitational force is pulling straight down, mg, where g equals the vector 0, negative 9.80. Now what's touching that? Well, the plane's touching that. And so this exerts a force like that right here. Now we have two kinds of contact forces. We could break forces into two groups anyway. Calculated forces, where I can actually calculate the value, and then constraint forces, where I cannot calculate. I don't know the value of this normal force unless I know something about the situation. So let's go over all the forces that we know. We know I'll call this Fg. This is the gravitational force on the surface of the Earth, mg, just like over here, and this is in newtons per kilogram. So this says that the gravitational force is constant and down. Okay, but that's just an approximation. The real gravitational force is F big G, and that's going to be equal to G m1 m2 over r squared r hat negative. So r hat is a unit vector. I should have done that in the previous case, but r hat is the vector r divided by the magnitude of the vector r. M1 and M2 are the two masses interacting, and then r is the distance between their centers, the vector between their centers. So if you're on the surface of the Earth, M1 could be the mass of the Earth, r would be the radius of the Earth, and g is a gravitational constant. G is 6.67 times 10 to the negative 11th newtons meter squared for kilogram squared. It's a gravitational constant. We have the Coulomb force, F, I'll call it C. This is we'll write it as 1 over 4 pi epsilon naught Q1 Q2 over r squared r hat. So this is the electric force between two objects with charge. It looks a lot like the gravitational force, except it deals with charges. And there's no negative sign. There's a negative sign here because they're attractive interaction. This could be attractive or repulsive. If they're the same charge, if Q1 is equal to Q2, the sign, then they repel. Okay, the only attract if one of them is negative. We have the force due to a spring. It's going to be, you can write that as, this is the best way to remember it. F spring magnitude is K times S, where K is the spring constant, the stiffness of the spring, and S is the stretch. If you want a vector value for that, which I don't think you're going to need for like the test, it would be F spring equals negative K L minus L0 L hat. So this is L is the length of the vector, and L0 is the unstretched length of the vector. Thinking of other forces. I just want to, friction, I guess. And I don't know that I'll put a friction thing on there, but friction's complicated. The frictional force, we have F friction static, less than the magnitude is less than or equal to the coefficient of static friction times the normal force. F friction kinetic is equal to the coefficient of kinetic friction times the normal force. Those are all your these are actually forces of constraint because they deal with the normal force. The normal force is the force that two surfaces are pushed together. You know, I was thinking, hey, I'm going to make an hour-long video, and I'm really getting kind of, I don't know if I'm going to make it. I'm going to make it for you. Okay. I want to take another break, but okay, let's get working. I want to talk about some fun stuff. Let's talk about the momentum update principle, because this is really important, right? If I have this as my momentum principle, and I can write that as F net is delta P over delta T equals P2 minus P1 over delta T. Now if I multiply both sides by delta T and add P1, I get P2 equals P1 plus F net delta T. This is the momentum update formula. This says that if you know the momentum and you know the force acting on an object, you can find the new momentum. Even if the force is not constant, this can still work as long as delta T is really small. This is what makes time travel possible. Oh, no, wait. I was thinking of the flux capacitor. This is what makes numerical calculations possible. This is how I solve problems with the computer, which I've done a lot of, but you know, some courses don't really use that too much. But this is huge. Now, I can also use the definition of average velocity. V average equals delta R over delta T, which looks the same way, and I can get the position update formula, which says R2 is R1, right? Because I'm going to multiply both sides by delta T and add R1. And then I'm going to, instead of the velocity, I'm going to say plus P2 over M delta T, because that's the velocity. And this is actually the velocity at the end of the time interval, and this is position update. But these two together are super powerful. If you have a changing force, I can use that force, I can calculate the force, use it to find the new momentum, use that to find the new position, and then go back up here and keep redoing it, and you can do magical things. Okay, you really can. Let's talk about circular motion. Yeah. You know, one of the things, let me say one of the things in here, this. This is, you know, the name of the book is called Matter and Interactions. And the idea, one of the big ideas here is that you can represent matter as a bunch of masses connected by springs. And this is a very powerful idea. Very powerful. And it works really well. Okay. But if you do this, then you need to somehow make a connection between the macroscopic properties of an actual material and the atomic properties, where these are the atomic masses, the atomic distance between atoms, and the interatomic spring constant, which isn't real, right? But we were going to pretend like it's there anyway. So this is equal to KSI over D. So Y is Young's modulus. It tells you the stretchiness of essentially the stretchiness of a material independent of the shape. So this is the force applied divided by the cross-sectional area of the object divided by the change in length over the natural length. And this reduces the Young's modulus as a property of the material, not the object. And we can relate that to the interatomic spring constant SI divided by D, which is the atomic diameter. And so that's a kind of a big idea. There's not a ton of questions that I can ask on that. So if you don't, you know, it's not something, I think it's a big idea, but it's not usually on a real big test question. Okay. So let's talk about this circular motion. Let's say we have an object, some velocity, moving in a circle at a constant speed. In that case, I can write F net magnitude, if it's moving at a constant speed, is equal to the magnitude of the change in momentum with respect to time. I have to take a derivative because it's constantly changing. But that would be equal to m times the magnitude of v squared over r. So this says, and I derived this somewhere else, so I don't want to work on it right here. But if an object's moving in a circle, then it'd have this as the change momentum. And the direction that change momentum would be towards the center of the circle. Okay. So if an object's moving in a circle, then that's true. We can also write this as m omega squared r, where omega is the angular velocity V over R. Okay. Yeah, there's some other stuff in there, but I'm trying to go with the basics, the most important things. Okay, time for break number 2. You know what this is? This, and I'll take it out of the box. It's a meteor. My brother got this for me for a present. You can buy these online. They're not super expensive, but they're, for me, I'm fascinated. This thing was in space, and now it's in my hand, and I could lick it if I want to, right? I'm gonna lick it. No, I'm not gonna lick it. But I really think that's awesome. Thinking of holding this thing that was in space. It's just amazing. Now, it's actually not. My hand was in space too, right? Most of the stuff in my hand is made from an exploding star. So, you can't. Where did all the atoms come from that we have? They're all from. We're made from interstellar stuff anyway. So maybe that's not so cool, but I like this. And I like to think of it like, kryptonite or something that gives me superpowers or takes away superpowers. I don't know. It's cool. Put it back in the case so I can pretend like I don't touch it when I actually do. Okay, I have one more thing to show you. But let's talk about the work energy principle. Okay, we already said work is a change in energy. And we said work is F dot delta R, and that's equal to the integral from 1 to 2 of F dot dr. One of the most important things when you do a work energy problem is, one, decide to do work energy, right? Decide to do work energy because it's you don't care about the change in time. You only care about the change in position. The next thing you need to do is say, what is my system? Because once you pick a system, we can look at work done on the system and changes in energy for the system. And that is important. And let me just go ahead and jump into the big thing here. We have two kinds. We have the point particle system, and then we have the real system. So in a point particle system, work is equal to F dot delta R center of mass. And I'm going to show you an example in just a little bit. So I take the forces acting on the system, and I use the displacement of the center of mass to find the work. And that assumes that the system is a point. Now, in the real system, I say work equals F dot delta R F. This is F dot the displacement of how far the force is applied. Let's go ahead and do an example. This guy's going to jump like that. So here's the center mass, here's the center mass. Now, if I use the point particle system, I have a couple of things. One, I have the gravitational force. And then two, and it's right there too. And then two, I have, let's say it goes up to here when they lose contact. I also have the force of the floor. And let's call this distance d. That's how far your center mass moves before leaving the ground. So if I do the point particle system, the work is equal to the force of the floor minus mg, plus, because mg is down, dot the vector, I never talked about the dot product, dot delta r. So let's talk about the dot product real quick. A equals ax, ay, az, b, bx, by, bz. A dot b. Okay, so you can't multiply two vectors. You can add vectors, you can't multiply them. We have two operations on vectors. One is called the dot product or the scalar product. And in that case, what I do is I take the x components of the two vectors and multiply them together. So ax times bx. And then I take the y components and multiply them and add them together. Add them to that. ay by plus az bz. So in the end, I get a scalar value because the components are all scalars. Now there is another way to do this. I can take the magnitude of A times the magnitude of B times the cosine of the angle between them. And that gives me the same thing. So if I do this with the dot product, I'm going to get, because delta R is going to be equal to the vector 0, 0, 0, D, 0, then I'm going to get F floor minus mg times D. And that's equal to the work in the point particle system. And that would be equal to the change in kinetic energy of the jumper. And that's cool. That works. You could actually solve for the force of floor. But if I take the real system, I mean, this says that the person has an increase in kinetic energy, which they do, and it comes from the floor. Because the floor does work on the person. That's not really true, right? The floor doesn't do work on the person. This is just an approximation. This is a lie. That's what that is, a lie. So when we look at the real system, this is PPS. In the real system, work equals the force. And let's just deal with this in the y direction. So I still have the same force, F floor times. Well, now I need to go in the how far did the floor move, right? So F dot delta R floor. Well, the floor didn't move. So this is 0. So the work done by that is 0. But then I do have the minus mg times d, which is the work done by gravity, equals delta k. But you see here, if the person's speeding up. So if the person's speeding up and gravity does negative work, then how does that happen? And the answer is that in the real system, the floor doesn't do work, but we have some other change in internal energy. You can have other energies. In a point particle system, you can only have kinetic energy. Okay. So in this case, this is a decrease in internal energy because the person ate breakfast or used their chemical energy from eating or whatever it is. Okay, let's talk about potential energy. Okay, so let's think about this. Work equals delta E. If work equals 1 to 2 F dot dr, if does not depend on path, this is the longest video I've made so far. So far, right? You never know what I'm going to do later. Depend on path. Then we call that a conservative force. And in that case, I can actually move this integral to the other side of the equation. So this becomes 0 equals negative the integral from 1 to 2 F dot dr plus delta E, whatever other kind of energy that I have. And we call this work in that case a potential energy. So delta U is the potential energy, would be negative the integral 1 to 2 of F dot dr. And so if we integrate one time, I can use that same expression for a lot of different cases. And I'm not going to do the integrals. I've done them before. But here are the popular ones that we get. We get UG, which is the gravitational potential energy near the surface of the Earth. And it's mgy. Now, we write this, but we only see a change in potential. Okay, so this doesn't really make sense on its own. It's when you put it in the equation, you would have work equals, you could get something like work equals a change in kinetic plus change in spring potential energy plus change in gravitational potential energy, or something like that. Okay, you can still have work done, but you can't have work done by gravity if I also have potential energy in gravity. Okay, that'd be like having cake and eating cake too, and everyone knows you can't have cake and eat cake too. Another one is the spring potential energy, which is 1/2 k s squared, where s is the stretch or compression of the spring, k is the spring constant, ug negative g m1 m2 over r. This is the gravitational potential energy for objects where the gravitational force changes. This is only near the surface of the Earth, but this works everywhere else. Those are the most common ones that you're going to see. We do have other types of changes in energy. Delta E thermal is mc delta T, the change in temperature. I don't think that's a huge idea. It's kind of cool, but I should say power. Power is the change in energy with respect to time. This is the rate that you do work, or the rate that you change energy, and this is in, if that's joules and that's in seconds, this is in watts. Okay, I think I'm pretty good. I think we can go on to the last principle, which means I can talk about my last item here. I don't know if this really helps, if you like this breakup thing, but I'll show you this. See, there's the hint right there. This is New York Comic-Con 2017, and this is my 4-day pro pass, signed by, I can't tell who all signed it. I don't remember. I know that it's John Lung, Brian Loudon, and I can't remember their names right off the top of my head. They're really cool guys. 2 of the cameramen for Mythbusters. So John Lung and Brian Loudon are the second Mythbusters, and don't diss them because they're awesome. And I went to Comic-Con and gave a panel discussion with them, and we decided to sign each other's passes. So this let us go anywhere in Comic-Con, which I thought it was really cool. Comic-Con's really cool because it's ginormous. New York Comic-Con was huge. Everyone had great costumes. There was so much to see. I didn't really get to see everything, but I had a great time. It's something that it's kind of overwhelming. I don't know if I could. I mean, I'd like to go back, but as a participant, it's pretty tough. It's pretty tough because it's a lot. There's a lot there. So that was a great adventure. I really had a good time, and we signed these to remember each other, and I keep that hanging up. So Comic-Con, Mythbusters. Yes. Oh, in case you didn't know, I did the panel for John and Brian because I'm the technical consultant or the science advisor for Mythbusters. So I did the last 5 seasons with Adam and Jamie. I did Brian and John. I did Mythbusters Jr. So I worked on that show, and you can see me in the credits if you look closely, but it goes by really fast. So there's that. Okay, let's talk about the last principle, angular momentum. Angular momentum. Okay, let's start off with the cross product. So if I have AX, did I have I had a little right-hand rule thing somewhere around here. Oh, shoot. I'm not prepared. I should have thought about that. I made one. Okay. Oh, well. AX, AY, AZ, and B is BX, BY, BZ. Then I have this operation called the cross product, or the vector product, A cross B, and it is equal to the determinant of X hat, Y hat, Z hat. I don't remember this either, so if you forget this, it's no big deal. We all forget this. AX, AY, AZ, BX, BY, BZ. So if I do that, I get A cross B equals, okay, so I'm going to expand about this row, and I get AY times BZ as my X component, AY BZ minus AZ BY. Now for my Y component, I'm going to expand about this, but I get a negative sign. There's this is Jacobian, which is -1 to the ij power. So this is actually, we have a negative sign in there. So I'm actually going to get AZ BX minus AX BZ. And then for the Z component, I get ax by minus ay bx. There. Now I can find the magnitude of a cross b, and it's the magnitude of a times the magnitude of b times the sine of the angle between them. And the other important thing is that if I have vector a and vector b like that, then the cross product a cross b has to be perpendicular to both a and b. Now there's only two vectors that do that. Okay, there's this one that comes out of the paper, see, because that's perpendicular to a and b, and then one that goes into the paper. And we use our right hand rule. See, that's my right hand. And if my fingers cross a and then b, my thumb would point in the right direction. So a cross b would be this way. Okay, that was a lot. So we need that for torque. So torque about some point O is R cross F. So let's just draw that. Because this is easier. Suppose I have this wrench and I pull with some force F right there. That's F, that's O, point O, and that's R. And so in this case, R and F are perpendicular, so theta is 90 degrees. So the torque would just be R times F. What if I change this so I pull this way with the same force? In that case, it wouldn't give me as much torque. You're not going to pull on a wrench at an angle like that to make it twist. It just doesn't work that way. So you can see that as theta gets closer and closer to 90, you get a better value. What if I pull over here instead? If I cinch up on that, that's going to give me less torque because I'm decreasing the torque arm R. Now, there's actually three ways to calculate the magnitude of the torque about that point O. I could say R F sine theta. I could say R perpendicular F, or I could say R F perpendicular. So so if I have this force right here, I can draw a line back right there, and there's my R perpendicular. Or I could go this force and find the perpendicular component of F. Those are the same thing. Okay. But the key here is that torques matter where the force is applied, not just what the force is applied. You can imagine right here, if I push with equal forces in opposite directions on this pin, the net force is 0. So the center mass isn't going to change its motion, but it will rotate. Okay. So torque, that's torque. And I'm flying through this. Okay. We did not spend a ton of time on torque and angular momentum, but there will be a question on the test. For my class, I'm going to give you an option to not answer one of the questions. So if you don't want to do angular momentum, you can do that. I'd be sad, but you got to do what you got to do. So that's torque. And torques are like rotational forces. They change rotational motion. So that means I have the angular momentum L is R cross P. But if I have a whole bunch of masses, I actually can write this as I omega. Now this, and so I is called the moment of inertia. It's the sum over I of mi/ri squared. It's a measure of how the mass is distributed about the rotation axis. This is true. This is true. L equals I omega. And omega is a vector that shows the axis of rotation using the right-hand rule. Now, if the axis of rotation is fixed, then this is the moment of inertia. Otherwise, then it gets way more complicated, but we're not going to do that in this class. Okay. So that gives me torque equals delta L over delta T. Let's talk about one last thing. And if you've made it to the end of this video, then you need to give yourself like a high five. Like that, okay? Because I'm not going to make it through it, and I know physics really well. Okay, let's say this. When is momentum conserved? So let's say I have two balls going like that, and they crash, and they bounce off like that. If I take my system of the two balls, then F net equals 0. And that's the change in momentum of the whole thing over t. So that means that it takes some time to collide, but the change in momentum is constant. So that means the initial momentum of the whole thing, let's call this A and B, A and B. The initial momentum is PA1 plus PB1 is equal to the final momentum, which is PA2 plus PB2. This is conservation momentum. It's true if there's no external forces. The momentum before the thing happens is the momentum after the thing happens. So you could get rid of these PIs and PS. PA1 plus PB1 equals PA2 plus PB2. Conservation momentum. Okay, conservation of energy. Work is a change in energy. If I pick a system where work is 0, then delta E is 0. And this could be any types of energy. So that means that E initial equals E final, and energy is conserved. Conservation of angular momentum. So torque net equals 0. If I pick a system such that the net torque is 0, then the change in angular momentum with respect to time is 0. So L initial equals L final. Angular momentum is conserved. Okay, so these are these are the three big ideas, because for every one of them, if we pick a system such that there's no external interactions in terms of forces, work, or torque, then we could get something conserved. And that turns out to be very useful in physics. So conservation, angular momentum is conserved only if there's no torque. If you're doing a problem and you're using conservation of angular momentum, then you better say in that solution, this is true because there's no net torque. Okay, I'm looking at my equation sheet and seeing if I need anything else in here. Constants and things like that, the speed of light, the electron mass. I'm not going to have you memorize those. That's kind of trivial. I wouldn't want to do that. I give you the equations that I want you to know. This is a test I'm giving you online because of the pandemic. But normally I would give you an equation sheet. So I think I'm just going to end there. I don't have any other toys to play with. So I'll if you like the toys or the little short story breaks, I'll make some more of those later. But hopefully this gives you an idea of the things that you need to focus on in the very short amount of time you have before the test. I probably should have made this a lot earlier, but you know me. So good luck on your final exam, and I will see you later.